Hi, welcome to Unit 5, Lesson 6, More Than Right. So for the ready, it says find the area of each triangle. Remember, the area of a triangle is equivalent to half the base times the height. So these triangles are already drawn with a height shown in for us, so we just need to figure out that height. Here we see we have a 45, 45, 90 triangle. So we can use our knowledge of 45, 45, 90, those special right triangles, that whatever the hypotenuse is, let's say this is BB, this is going to be B root 2. The hypotenuse is root 2 times the length of the two sides. So since we have 5 root 2 centimeters, that means the height here is 5 centimeters, and so is this length, but we don't need that length. Because the triangle we want to find the area of is this whole big triangle, and we already know that 14 centimeters is the base. So for this one, we can say that the area is 1/2 times our base 14 times our height 5. Well, 1/2 times 14, that's 7, and 7 times 5 is 35, so the area is 35 centimeters squared. Problem number 2. Here we have a 30, 60, 90 triangle. We see the hypotenuse is 18, and remember the ratios for the 30, 60, 90. And there's a bunch of ways you can really depict these ratios. Let's say this is the 60 up here and the 30. Well, I'm just gonna say that our hypotenuse, if it's 2, let's say 2 times something, that means the side across from 30 is always half of that. And then the side across from 60 is square root 3 times the side across from 30. So if we know the hypotenuse is 18, that means, 30 is across from this height. So our height must be half of 18, or 9 centimeters. So for here, our area is going to be 1/2 times our height, 9, times our base, 38. Right, this is our base, since that's where our height is connected to. So 1/2 times 9 is 4.5, although I think it's easier to do 1/2 times 38, which is 19, and then 19 times 9 gives us 171. So the area is 171 centimeters squared. Problem number 3. So another special right triangle, we see a 60-degree angle, which means we have a 30. We see our hypotenuse is 14, which means this side down here is 7, which we don't need. And this side right here is 7 root 3, which is our height. We see that 90-degree angle, so this is an altitude. So area, we have 1/2 times 7 square root 3 times 11. Now this one I'm going to pull a calculator out for. So let's see. 7 square root 3 gives us approximately 12.12, right? So 1/2 times 12.12-ish times 11. That's going to give us an area of 66.7 centimeters squared. Let's just make sure the directions didn't say to round any specific way. It didn't, so I'll just go to 1 decimal place for now. Okay, let's move on to question 4. Question 4, another triangle here. This one's isosceles, so it's not a special right triangle, but I see that we have these two side lengths the same, which means these two angles must be the same. So we actually have two congruent triangles here, and there's a few ways, right? We have this reflexive side in the middle, so we could say that we have these two sides, and we have another 90-degree angle, so it could be angle, angle, side, or a few different ones. we could use here to determine that these are two congruent triangles. Since they're congruent, that means this side length and this side length must be equal. Well, we know there's 16 total, which means each one is 8. Now, this is really helpful for this because we need to find this height. So to find that height, we can use tangent. So we can say tan of P, which is 70 degrees, is equal to opposite, which is our height, over 8. So if I need to find my height there, I can do 8 times tan of 70 degrees. So that's going to give us our height. We already know our base is 16. So let's pull out our calculator. Since tan of 70 isn't an exact value I can do in my head, we could round it. We know it's going to be near 2 since we know tan of 60. But tan of 70 is about 2.7 times 8. So we get a height of about 21.97. Let's just round up to 98 there. So that's our approximate height. So that means our area, we're going to take that height, 21.98, and multiply it by 16. And then remember, we're doing half, so we're really multiplying this number by 8. So 21.98 times 8, we have an area is 175.83. So I'll just go to 8. And here we have centimeters again, so centimeters squared. Okay, question 5. We're back to special triangles. We have 30, which means this is 60. Well, if our hypotenuse is 24, the side across from 30 is 12. This time we don't know our base, right? We have to figure out this base. However, it tells us that this is isosceles, which means this triangle on the right side. So that means the side is also 12 right here. And since this is across from a 60 angle, we can say that this side is 12 root 3. So our base, we're going to add those two values together. 12 plus 12 root 3. So our base is 24 root 3 centimeters. Right? We know our height is 12 centimeters. So our area is 1/2 times 12 times 24 root 3 centimeters squared. Right, so that gives us 1/2 times 12 is 6. So we do 6 times 24, which is 144. So 144 root 3 centimeters squared. So let's get, that's a square. Let's get a decimal approximation there by multiplying by the square root of 3. So times the square root of 3 is going to give us an area of approximately 249.41. So I'm just going to go to 4 centimeters square. So we have our exact and our approximation. And we're going to backtrack because I just realized I made a very, very silly mistake here. Let's go back to sort of this part here. This is true. I added those two numbers together when I really couldn't add them together because the root 3. So let's be a little more careful there. Let's just actually do 12 root 3 out first. We don't need it to be exact values. So 12 times square root 3 is 20.78, we'll say. We'll round to 2 decimal places, which means we're going to multiply these values by 32.78, and we add that 12 to it. And 32 times 12 times 2 does not give us the number I said before. It gives us, hold on, let me actually pull out my calculator to make sure I do that accurately. 32.78 times 12 times 1/2, we're going to get 196.7. 196.7. Now it's 707, so I'll just keep it at 7. And we're in feet, we're not in centimeters, so I don't know what I'm doing here. So I apologize for this problem. We went all about it wrong. Sometimes that's good. Sometimes it's nice to see if maybe you got that answer that we had before, and now you can see why that doesn't work. That we just added those two numbers incorrectly. Okay, let's move on to problem 6. So problem 6 is the start of our set problems. Students in high school mathematics class were given the following problem. While traveling across a flat stretch of desert, Joey and Holly make note of the top of a butte in the I could be saying that wrong. Butte in the distance that seemed to be directly in front of them. They estimate the angle of elevation to the top as 5%. After traveling 6 miles towards the butte, the angle of elevation is 25 degrees. Approximate the height of the butte in miles and in feet. And it tells us the conversion for miles to feet. Use the given values to solve for x in miles and d in both miles and feet. And it tells us we can estimate tan of 5 is about 0.1 and tan of 25 is about 0.5. So let's start by drawing this image. They actually already draw us the image. If we look down, we have a little image to go off of. So let's start analyzing this. Okay, so we can actually set up a little system of equations since it tells us we know what tan of 5 is and tan of 25 is, and it already put in our angle of elevations for us. We see that, and we see where they put the 6, the x, and the d. So let's start. I'll kind of write this one up here. So tan of 5 degrees. Well, that's opposite. And remember, we want to use the right triangle. So I'm going to ignore the fact that this is an angle here. I'm going to say opposite is D, but now I have to be careful since I'm using the right triangle. My whole adjacent side there is 6 plus x, or x plus 6, doesn't matter the order. We also know that if we use tan of 25, well, opposite is still D. And this time, since that's a much smaller triangle, the adjacent side is just x. So let's substitute our tan of 5 is 0.1. So 0.1 equals d over x plus 6. And here, it tells us tan of 25 is 0.5, so use 0.5 equals d over x. So let's isolate d in both of these equations. I could have picked either variable, but I'm going to isolate d. So I'm going to multiply both sides by x plus 6 here. So if I multiply 0.1 times x plus 6, I get 0.1x plus 0.6. equals d, and I get on the second equation I get 0.5x equals d. So since both of those values are equal to d, I can set them equal to each other. I can say that 0.1x plus 0.6 equals 0.5x. Like that, 0.5, 0.6. There we go. So now I want to isolate the x, so let's move this 0.1x over. 0.1x over, we're going to subtract it from both sides. So we have 0.6x equals 0.4x. You can multiply, if you don't want to deal with the decimals, just multiply everything by 10, which really gives us 6x. Nope, not 6x. Why did I add an x there? 6 equals 4x. So if we divide both sides by 4, we get 6 over 4, or 3 halves for x. So we get 3 halves. So remember, x, if I look back up, it says x is in miles. So for this problem, I'll write my answer up here. X is 1.5 miles, or 3 halves miles. 1.5 miles. So that's our answer for x. Now let's go ahead and find d. Well, now that we know x, we can use either equation. I'm going to use this 0.5 equals d over 1.5 to find my d value. So I multiply both sides by 0.5, by 1.5. Now I'm actually going to turn these to fractions. I just think that's a little bit easier to look at. So 1/2 times, or let's do equals d over 3 halves. Well, to get rid of this 3 halves in the denominators, I can multiply by the reciprocal, or really divide by the 3 halves. So I'm gonna. I think I just said that backward actually, but I'm gonna multiply both sides by 3 halves. That's gonna get rid of my 3 halves there. So I'm left with 3/4. Sorry. 3/4 for D, which is about 0.75. Now remember, this is in miles, since this right here is miles. So D is 0.75 miles. So let's figure that out in feet. Well, to figure it out in feet, we multiply by, 0.75 times that 5,280 is going to give us our feet. Because we're really thinking, if we want to really see how that conversion comes about, 0.75 miles over. So I want to say, okay, 1 mile is on the bottom here. That's why they're going to cancel out. So 5,280 feet. We're only left with that units of feet. So that's how we can remember the way we want to convert. So 0.75 times 5,280 gives us 3,960 feet. So there's our answer for D. Okay, let's move on to problem 7. I know my work is kind of all over the place there. Let's clean it up just a tiny bit before we move on to 7. There we go. It's a little bit neater there. At least it's kind of all in the same problem. So problem 7 actually wants us to use problem 6. It says rework problem 6, this time using tan of 5 equals 0.0875 and tan of 25 equals about 0.4663. Or use the values in your calculator without rounding them. So it's saying use more exact values, like 0.5 and 0.1 were very rounded numbers. So we're going to come back to our sort of initial starting statement. We started with this, so we can start with that again, because the image hasn't changed. It's just the values that we're using for tan of 5 and tan of 25 are going to be a little bit different. So we're still going to have this, let me zoom in a little bit so I can write a little neater. We're still going to have this D over x plus 6 equals tan of 5 degrees. And we're still going to have this D over x equals tan of 25. That hasn't changed. It's just what values are we substituting for our tan. I'm going to make this a little smaller so I can fit a line underneath it. So now we're going to do D equals x plus 6. And it says use tan of 5 equals 0.0875. Now I'll end up typing this into my calculator and not rounding at all. But for the sake of sort of showing the work, I'll put that there for now. And D equals x times, well, we're going to use 0.4663 instead of x. So we get those two things when we input our tan. So those are the two values we're going to set equal to each other. So let's move this over here. We're going to substitute for D. So we're going to have 0.0875x plus, well, let's see what we get when we do tan of 5 times 6 in our calculator. Tan of 5 times 6 gives us 0.5249. And I'll use 4 decimal places since that's what they give us here. But ideally, instead of clearing our calculator at all, we can do this all as one step. So 0.4663x. Okay, so let's combine our like terms. Let's subtract. So 0.0875x, I'm going to move over. And I put my decimal place in the wrong spot there. There we go, 0.0875x. So if you want to be more exact, you can actually just do tan of 25 degrees in your calculator minus tan of 5. Remember, that's where these two values are coming from. So if you want to do that in your calculator, you'll be a little more exact. So if we subtract those two values, we do get about 0.3788. Now, since we're just rounding to 4 decimal places, you get the same thing whether or not you use your calculator to do it using tan of 25 minus tan of 5, or just 0.4663 or minus 0.0875. But now that I have that number in my calculator, the number in my calculator I have isn't just 0.3788, it's 0.3788189 and so on, which allows me to be a little more exact. So now let's go ahead and divide by that number. To get our x by itself. Okay, once I do that, I get about 1.3857 and so on. I'm going to make this a little smaller so I can fit that underneath. Okay, good. So x is, what is our unit here? Oh yeah, miles. So my pen is not writing. Hold on. Up there it goes. Okay, 1.3857. Now the next number is 0, 6, and so on. So I'll go to there. So miles, because we only need x in miles. So there's our miles. So now we're going to plug this in to find d. So last time I used this equation right here, although I don't want to use the 0.5, I want to use our more exact value. So I'm going to use this right here. Let's highlight it so you can see. I'm going to use our d equals to figure out what our d is. So d equals 0.4663, or tan of 25, times 1.3857, and that's going to give us our d value in miles. So d is, let's pull out our calculators. So I'm going to I haven't cleared my calculator yet, so I'm going to take that exact answer and multiply it by tan of 25, which gives me about 0.6462. I'm rounding that. It's 64616, so I'm going to round up to 2 miles. So that's miles. And d is, remember, to get that number in feet, I have to multiply by, let's see, 5,280. So 5,280 times our 0.646, we get about 3,411.75. And I'll keep the 4 decimal places trend we've been going with. So 75, it goes 436. So 75436, I'm going to round that up to 4. And that is our conversion in feet. So if we look, they're pretty similar answers, right? We said it was 1.5 miles for x, and this time we know it's a little bit closer to 1.3857, right, or about 1.4. D, we said it's 0.75 miles. Well, it's actually much closer to 0.64 or like 65-ish. And then instead of almost 4,000 feet, we realize it's about a little less than 3,500 feet. So those answers are more exact. Kind of goes to show you how big of a difference rounding can make in some of these problems. let's move on to problem 8. So it says, the situation problem 6 included approximating angles. Surrounding didn't matter very much. Consider a situation where Joey and Holly were serious rock climbers and were planning on scaling the face of the butte, and they had used an inclinometer to measure, again, I could be pronouncing that wrong, to measure the angles of elevation accurately. Describe the difference between rounding to 1 decimal place and rounding to 4 or more decimal places. So we did just talk about that a little bit. And to tell us what an inclinometer is. It's an instrument used for measuring angles of a slope, elevation, or depression of an object with respect to a plane. So in this case, basically, rounding to 1 decimal place, to 1 decimal place caused them to really overestimate. The distances, but by a pretty substantial amount, right? Like we said, for D, the height there is 3,411 for one, almost 412, versus 960. So we're overestimating by over 500 feet. By over 500 feet, and I could have picked the miles and gone with miles too, but that's a substantial amount to overestimate. So that's the difference in rounding, that a lot of these, especially with situations like this, you want to be exact. As our values get bigger, those overestimations are going to become more severe. So we really want to try to be more exact by using exact values whenever possible. Okay, question 9. The Star Point Ranger Station and the Twin Pines Ranger Station are 30 miles apart along a straight mountain road. Each station gets word of a cabin fire in a remote area known as Ben's Hideout. And we see that. We see all those places labeled on our diagram. A straight path from the Star Point to the fires makes an angle of 34, so we see that angle labeled, degrees with the road, while a straight path from the Twin Pikes makes an angle of 14 degrees with the road, so we see that angle. And it wants us to find the distance d of the fire from the road, so it wants us to find this height. Okay, so there's a few ways we can go about this one. We could recognize that we have 2 right angles here. Or 2 right triangles, I should say, and 2 right angles. There's a second right angle right there. And we could make 2 equations with d. We could say that, let's say this is x and this is 30 minus x. So if we want to avoid anything other than right triangle trig, we could absolutely go about saying that. And we could say tan of 34 degrees equals d over x, and tan of 14 degrees equals d over 30 minus x. So very similar setup to the last one. We also could figure out what this angle here, and we could go ahead and use our law of sines if we wanted to. So I'll show that after. So here I'm gonna multiply. Let's get d. Let's isolate d again, since we want to find x anyways. So d equals tan of 34x, and d equals tan 30 minus x times tan of 14. I'm sorry. So now that those are both equal to d, and we see that d is the same height, we can set those equal to each other. And I just misspoke before. I said we don't want to find d. That's the one we are trying to find. So it actually would have been nice to isolate x instead. So let's do that. Let's isolate x. So x equals, here I'm going to cross multiply and get d over tan of 34 degrees. There we go. And here I'll use what we have already. I'll distribute that tan of 14. So 30 tan of 14 minus tan of 14x. That allows me to subtract. So I can do d minus 30 tan of 14 divided by negative tan of 14 to get x all by itself. So now I can set these two things equal to each other. I can say d over tan of 34 equals d minus 30 tan of 14 divided by negative tan of 14. And you could have just found x first if you found that easier, perhaps. So from here, we have d in two places, so we want to try to get that together. Let's cross multiply. That's a nice quick way of getting rid of our fractions to start. So that gives us negative tan of 14d equals tan of, I'm going to distribute this tan of 34. So d tan of 34 degrees minus 30 times tan of 14 times tan of 34. And this is certainly not the fastest way to get our results, but it is one way to do it without using any type of right triangles. And I'll show it a few different ways, and you can always fast forward to whichever way you prefer. So now let's get our d's on the same side, right? I have d here. So let's actually, I'm going to move this d over, move this 30 over. That way we have positive terms. So 30 times tan of 14 degrees times tan of 34 degrees is going to be the same as d times tan of 34 plus d tan of 14. So now that I have a d on both sides, I can factor out my d. So 30 tan of 14 degrees times tan of 34 degrees equals d times tan of 34 plus tan of 14. And if I really wanted to, I could actually use some properties to combine these tangents. But I'm just going to divide everything by this tan of 34 plus tan of 14. So if I divide that, it goes away. And there we have it. We actually just have to plug all this into our calculator. So we do want to make sure we're being extra careful when we're plugging it in. I'm going to add a second set of parentheses right here just to make sure when I do my divisions, I'm not making mistakes. So let me pull my calculator out. Okay, when I carefully plug this in my calculator, I get about 5.46. We can go to 3 decimal places, I guess. So since it's 5.461, I'm going to go to 461. So 461 equals d. And since our distance is in miles, find the distance. So about 5.46 miles. Okay, and there's question 9. Let's just clean this up a little. And get it all kind of in one area. There we go. Okay, so like I said, I said I would show this using a different method, right? We could do law of sines, but we haven't quite gotten there yet, so it's nice to do this another way. But I could have actually solved for x first, right? So one other method would be to, or solve for x first. Then plug that in to find d. So I'll do this over here. So x first makes the math a little bit less, there's just a little bit less going on. So if x equals d over tan, or I should say solve for d first, or we're isolating d first. We are solving for x first. So d equals x tan of 34. And on this side, we get d equals 30 minus x times tan of 14. So if we set those two things equal to each other, x tan of 34 equals, I'm going to distribute again, 30 tan 14 degrees minus x tan 14 degrees. Then I can move my tan of 14 over. So it's now plus tan of 14 equals 30 tan of 14. And again, I want to factor out my x here, so I'm going to factor out x to get tan of 34 degrees plus tan of 14 degrees equals 30 tan of 14 degrees. And then I'm going to divide everything by tan of 34 degrees plus tan of 14 degrees. Again, just having parentheses makes that really nice and neat. I'm going to do that to both sides. So tan of 34 degrees plus tan of 14. Then we just go ahead and pop that right into our calculator to get x equals about 8.096. So 0.964, 9, so on. So that's our miles for x, which then we could use to say, well, we know x equals, actually, I'll start with this. I'll start with this one right here. So d equals 8.096 tan of 34. And that will give us our d equals about 5.461 miles again. So whichever methods kind of speaks to you more. You certainly don't need to do it twice. I just wanted to show both methods. So let me, I'm going to pause this and clean this up a little bit. Okay, so I just unpaused. You see everything's kind of magically a little neater. So our method 2 and method 1. And then, like I said at the beginning of this one, we're actually going to learn something called the law of sines eventually, which will make this problem much faster. But let's move on to problem 10. It says, in problem 9, we had two expressions that were both equal to d. Use both of those expressions and the value found for d in problem 9 to check your answer. And then it says, explain why they were not exactly equal. Doesn't matter if this application were real life, why or why not. Okay, so we used tan of 34 equals d over x. So basically it's saying let's use tan of 14 degrees equals d over 30 minus x instead. Now it's referring to if we did it this way. So this question is kind of dependent on how we solved it. So for this one, really this is if you used method 2. You used method 2 and rounded your values. So we did eventually round, but we did, or at least I kept things pretty pretty detailed in my calculator, right? We used 8.096. That is a rounded number. So let's say if we used, that instead of using 0.8096 times tan of 34, if we use this one, we would get D equals 30 minus 8.096 times tan of 14. So I multiply both sides by that 30 minus x. So if I were to use this one instead, this is a round value, so I'm going to do approximate. Let's pull our calculators out and type this in. So 30 minus 8.096 gives us about 21.904 times tan of 14 degrees. So D equals, so if I take this and I multiply by tan of 14, I get about 5.461. I'm going to go to another decimal place. I'll go to 5 decimal places here. 8. So I get 4.6128 miles as my answer. And that's going to lead me back up to this for a second. Let's go back to this. If I wanted to be a little bit more specific for answer 1, so let's go to question 9. Again, question 9. So if I didn't want to round so much, if I wanted to do 0.809 or 8 points, D equals 8.096 tan of 34. Let's see what that gives us. So let's see. We'll go to a few more decimal places. So 8.096 times tan of 34 gives us about 5.46082. And I'll go to one more decimal place, 1. So we see that the first 2 decimal places, those are exactly the same, but then it does start to change after the third. So it doesn't matter if this is applicable. Does this matter if this application were real life? Why or why not? I would say no. I would say this is a minute enough difference to not really matter. So this would be a relatively unimportant difference in real life, given this scenario. Right, we're going to assume no matter how this person is traveling to these 2 stations, that this is a relatively minor difference. When we're talking about 5.461 miles versus 5.460 miles. So a relatively small difference. However, if I had rounded to, let's say, 1 decimal place, that difference becomes bigger. If I had rounded to whole numbers, that difference becomes way bigger. So it really depends on how you round. So it depends on how you round. Depends on how much you round. So we kept a few decimal places, which made our answers substantially more closer. And in fact, both of these, if we round them to only 3 decimal places, we get the same value. We get 5.461. So to 3 decimal places, we can't even see the difference when we round, but to 4 decimal places, we can see the difference when we round. So we have to go pretty far out to see that difference. Okay, let's move on to our Go problem. So Go says solve for the missing sides and angles in the right triangles. And, right answers in radical form do not use a calculator. So we're using our special right triangles. So here I see I have a 45 degree angle, which means it's a 45, 45, 90. Now we can do this. Remember, we can kind of memorize these in a few ways. I can say b times root 2, and then this is b and b for that 45, 45, 90. Or if you prefer your hypotenuse to just be the sole value, then this would become b over root 2. B over root 2, which we never want to leave like that. We want to rationalize. So root 2, square root 2 times b over 2 for both of these. So square root 2 times b over 2. But it's okay to sort of think of it as this while we're doing our simplifications, because here if I use that method, then my b is 16. So to find this side, I need to think, okay, b over square root 2, well, that becomes 16 over square root 2. I'm going to rationalize by multiplying both sides by square root 2 over square root 2, which becomes 16 root 2 over 2, or 8 root 2. So both of these become 8 root 2. Okay, let's go to problem 12. So problem 12, we see that our two side lengths are the same and that this is 90, which means it's a 45, 45, 90 triangle. So again, let's say that if b is 34, then these side lengths are 34 divided by square root 2. I want to rationalize, so I multiply by square root 2 over 2. Which gives me 34 square root 2. I don't know why I wrote a 3 there. Square root 2 over 2, or 17 square root 2. Notice it's half the length of the hypotenuse times square root 2. So if you've picked up on that pattern, you can absolutely use half the length times square root 2. That works as well. It's a little faster, but it's more to memorize. Okay, 13 says, write the rule for finding the sides of an isosceles right triangle when you know the hypotenuse of the measure of the hypotenuse does not show a square root 2. So we kind of already did that. So the hypotenuse does not show. So find the rule. Well, we did that above. Let's kind of draw it again. That means we just want this to be sort of a 1, or 1 times some scale. I'm using b, but you can use any variable. So then this would be square root 2 over 2 times, let me zoom up so it's a little bit neater, square root 2 over 2 times b, and square root 2 over 2 times b. So we can think of it as half of b, right? So a good way to think of it is half the hypotenuse times square root 2. So that's a nice little way of thinking it. We're cutting that hypotenuse in half and then multiplying by square root 2. Okay, problem 14, we have our 30, 60, 90. So our ratio for 30, 60, 90, here we go. I'm going to draw it two ways. I'm going to say, let's say this is our 30-degree angle up here, and 60, which is different than the orientation that our drawing is, so let's just be careful. Let's say this is 2 times b. Remember, the side across from 30 is half of that value, so 1 times b. And the side across from 60 is half that value times the square root of 3, which gives us really just square root 3 times b. So that's one way to think of it. And I guess we can just start with that to start. Yeah, so this time we have the side across from 60. So we have 15 is in the place of this 3 times, square root 3 times b. So if I want to sort of figure out my b value, square root 3 b equals 15, well, I can divide that 15 by square root 3. Right, so there we go. Now, I never want to leave it in that form. I'm going to rationalize it. So I'm going to multiply by square root 3 over square root 3. So I get 15 square root 3 over 3. Whoops. And 15 divided by 3, I can reduce that to 5 square root 3. So that is my b value. So that's going to go right where the 30, on the side across from 30. So 5 square root 3. And remember, the hypotenuse is double this. So 5 square root 3 times 2, that gives us 10 square root 3. And if you want to check, you can always use Pythagorean's theorem and actually add these up together and see if you get it. Not a bad idea to do a little check. 5 square root 3 squared plus 15 squared. Is that going to give us 10 square root 3 squared? Well, 5 squared is 25. Times square root 3 squared is 3. So we get 75 plus 15, 225. So if we do 225 plus 75, we get 300. So 300, remember, that is 3 times 100. So if I were to take the square root of both sides, 10, I'll just multiply this out actually. 10 times 10 is 100. Times square root 3 times square root 3 is 300. So this checks out. We did do it right. It's a nice, doesn't hurt to sort of check your work as you go. If you're not confident, we didn't need our calculator for any of that, assuming we could, do some square roots in our head. Okay. So problem 14. So again, we have a 30, 60, 90 triangle. So let's change our color up here. So this is our 30-degree angle. So once again, we have the side across from our 60-degree angle. So square root 3b equals 24. So just like last time, we're going to divide both sides by square root 3. So 24 over square root 3. Let's rationalize this by multiplying by square root 3 over square root 3. That gives us 24 square root 3 over 3, which becomes 8 square root 3. So that's our side across from 38 square root 3. And we're going to double it to get our hypotenuse, 16 square root 3. We checked the last one, so we won't check that one. Let's go down to problem 16. It says, write the rule for finding the missing sides in a 30, 60, 90 triangle when you know the sides opposite the 60 angle, but the measurement doesn't show a square root 3. So for this one, let's think about what we. So now this one, find the rule for finding, find the rule for finding the missing sides triangle when you know the sides. So for the side across from 30, I'll just redraw a triangle, right? So 60, we know this is the same thing as square root 3b, and this is b, and this is 2b. So we divided the side across from 60 by square root 3, then rationalize. To get the side across from 30. To find the hypotenuse, we double the side we just got across from 30. Now, there's a few different ways you could think of that. If I wanted this to be, the hypotenuse is just b, then I could say that the side across from 60 is square root 3 divided by 2 times b. And then I would find the hypotenuse first and cut that in half to find the side across from 30. So other possible strategies as well. Okay. So find the missing measurements. So we have a 45, 45, 90 triangle here. And we don't have any side links. So all we can assume is that this is S. And whatever this is, it's going to be S times the square root 2. If we knew S, we could plug numbers in there, but we don't. So that's how we leave it. So let's go down to 18. We have a 30. So that means this is 60. So if we know the hypotenuse is H, that means whatever across from 30 is going to be half of H. So H over 2 or 1/2 H. And this is going to be square root 3 over 2 times H. We're going to take that half of H and then multiply it by square root 3. I think I said square root 2, but square root 3 over 2 times H. Okay, problem 19. It says fill in the ratios for the given functions. Do not use a calculator. Answers should be in radical form. Okay, so sine of 45, cosine of 45, and so on. So let's draw this 45, 45, 90 triangle. Now, I'm going to do this one as, I guess we'll just do 1, 1, square root 2. We could do it that way. Or we could make this one, and this is square root 2 over 2 and square root 2 over 2. So we can actually kind of choose to look at whichever triangle kind of works better depending on what we're asking to find, right? So our sine of 45, remember that's opposite. So let's say we're looking at this 45 or this 45. We could say opposite is 1 over square root 2. That one's not going to be rationalized for us. So instead, if we look at square root 2 over 2 divided by 1, then we don't have to do any algebraic work, right? Square root 2 over 2 divided by 1 is just square root 2 over 2. The nice thing about cosine is that these are the same since it's an isosceles triangle. So I can go ahead and say square root 2 over 2 there. Tangent, it doesn't really matter which triangle we look at. If I look at the opposite and the adjacent sides in this triangle, they're 1 over 1 or square root 2 over square root 2, since opposite over adjacent, so opposite over adjacent are the same. We're really just getting a 1, no matter how we look at it. So there's our 45, 45, 90. So let's draw our 30, 60 triangle next. So let's say that this is 30, 60, and then we have our 90. So let's call this 1/2. Let's call this square root 3 over 2, and let's call this 1. Again, we don't have to necessarily do it that way. We could say, I'll keep my 30. Oh, these are not to scale. I'm going to make it a little bit better, I guess. There we go, a little bit more to scale. 30, 60. So if I make this 2, then this becomes a 1, and this is just square root 3. So whichever one you prefer to look at. So 30 degrees, right? We're going to look at this top angle here. So for sine of 30 degrees, right, sine opposite over hypotenuse, right? 1/2 divided by 1, which is just 1/2. So that one's nice. If we're looking at our cosine of 30, so adjacent, square root 3 over 2 over 1, square root 3 over 2 divided by 1. Well, that just gives us a square root 3 over 2. And then tangent, I'm going to use the second triangle for tangent, I guess. It doesn't matter. So tan of 30 opposite is 1 over adjacent square root 3. But remember, I need to rationalize that. So I get square root 3 over 3. If I had used the other triangle, I would have had 1/2 divided by square root 3 over 2, and it would have came out the same. Okay, so let's now do the same thing with our 60-degree angle. I don't necessarily need to redraw it, but why not? I'm going to make these triangles more to scale. That's good enough. 30. Let's keep our orientation the same. Let's make this our 30 and our 60. So I'll keep the square root 3 over 2, 1/2, 1. And I'll draw both versions again. So 30, 60. What am I doing here? My apologies. 30, 60. So if I want this to be a 2, right, this becomes square root 3. This becomes 1. So we can look at either triangle. So sine of 60. So this time, if we're looking at the 60-degree angle, we're looking at this angle down here. So let's do sine of 60. Well, opposite 60 is square root 3 over 2. Hypotenuse is 1. So square root 3 over 2 divided by 1, which is just square root 3 over 2. Notice that's the same as cosine of 30. So cosine of 60, adjacent is 1/2, hypotenuse 1, so 1/2 over 1, which is just 1/2. And tan of 60, I'll use this other triangle here. So opposite is square root 3, adjacent is 1. So square root 3 divided by 1 is just square root 3. So there we have the 30 and the 60-degree angles, and that's it for this problem set. So thank you for watching, and I hope you found this video helpful.